Here's where we were last time. We were talking about change of variables. And here's the big idea. The big idea is we saw an example from single variable calculus, namely the substitution rule, where if you have a substitution function, we're going to reconceive of it now as a change of variables function, and if you look at some original domain, I'll call it, and then its image, right, then an integral over the image domain can be pulled back, is the terminology that we use, right? I can sort of, it's just plugging in, really. It's substitution. It's literally substitution. We're plugging in everywhere we see x's and y's in this blue integral. Just plug in for how x's and y's are known functions of u's and v's, and now you have an expression involving u's and v's, which is an integral over what I'm going to momentarily call the original domain. Now, of course, in practice, the way this comes up, it's not that most of the time we actually start with an original domain. I mean, in practice, what this is good for is the scenario where we start off with an image domain. That this is kind of our, in practice, original domain. And through the process of pulling back, we turn it into a new domain that I like to call the pullback domain or the pre-image domain. Okay. All right. So the big win is that now, instead of having to slice and dice this horrible domain here, where you can see I slice through a corner, right, and then I slice through another corner, right, or worse if you do it in the other direction, right, depending on how you slice. Instead of that, now I just get to slice and dice a good old, plain old-fashioned rectangular domain. Not only do I not hit any corners, right, but the bounds are constants. Life is good. As far as an iterated integral goes, you can't beat it for a convenient domain. Okay. All right. As I have it drawn in this case, now, of course, let me recognize not every pullback will have the feature that it'll be a rectangle. Sometimes the pullback domain will be something else. But hopefully, kind of the motivation for the process is that this is at least a better domain than this original monster, whatever that might be that we started off with. Usually that's the motivation. Okay. All right. So how do you do it? Well, again, it's a matter of plugging in. So x and y are functions of u and v. That's just what g is. That's the act of plugging in. Now, the act of plugging in, of course, goes, in terms of how it deals with expressions, it kind of goes backwards. When you plug in, x's and y's turn into u's and v's, and thus the sort of backward nature of how this pullback moves. Thus the name pullback. The only other detail you have to keep in mind is that when you're looking at the differentials, when you're looking at the pieces of area, you just don't forget that, well, in the process of taking a domain and looking at its image, little pieces of area get stretched out. It's highly relatable, right? Look at the domain on the left, look at the image on the right. The one on the right's bigger. It got stretched out a little bit, so you just have to keep track of how much areas got stretched out, and that factor by which areas get stretched out, uncreatively I call it the stretching factor, right? And so don't forget to plug that in. That's part of the plugging in. That's how we turn dx dy into an expression involving u's and v's. Okay, so that's the big picture. The detail that we're not going to prove for the moment, but that we will talk about later, is that stretching factor is the absolute value of the Jacobian determinant. Convenient notation for it is like this. We talked through those details last time, and off we go. So here's the example we started with last time. We had a change of variables function given. Now, lucky break happened to be the change of variables function was just straight up given. You won't always be so lucky. We're going to talk today about what do you do if it's not given, and what various versions of how to deal with that. And then following the rules, now of course the tricky bit was to figure out what is that stretching factor, and the stretching factor, well, I guess it's this whole calculation here. Stretching factor, highly computable. Just don't forget to plug that in, right? Our bit of area in the xy plane is a stretching factor that we just computed times du dv. Everything else is just plugging in. Okay. All right, that was from last time. Okay, we're going to see a few more examples. Hands dirty kinds of examples. Here's the next one. Now this next one is also kind of, there's something particularly convenient about it. And again, you won't always get this lucky, but stuff like this comes up surprisingly often. It's important to see these kinds of examples. Let's make the observation that this function here rotates points in the plane around the origin by an angle of theta. Now, why that is true is there's some details to be written down and discussed. If you're curious to confirm, if you'd like me to explain to you how you should know that this is what I say it is, there's a Math 216 point of view on this. It's really kind of the best point of view. But there's also a Math 212 point of view. If you're curious, come to office hours. I'll be happy to show you. I'm going to take it in this question that this is a given. And a lot of y'all are engineers in Math 216. We'll see exactly why this is true. Okay. Anyway, for the purpose of this question, this is a given. That's a rotation. We're going to use that rotation as a change of variables function. We're going to use that function to understand this domain, R, that is this given square with those 4 given corners. And now let's momentarily recognize that if I wanted to work out this integral sort of the old-fashioned way without using sophisticated change of variables techniques, right? Well, this is a stinky domain, right? I mean, look at the slicing process. You're going to slice through a corner there, and you're going to keep going, and then you'll slice through a corner there. And so this is 3 separate integrals. And also, if you slice the other way, still 3 separate integrals. So suboptimal. Let's hope that we can avoid doing that. So the big trick, big idea is with all this given to figure out how can I use this category of functions, this template formula for rotations, to do a pullback. Is this square a rotation of something nicer? Right? And you got to think creatively. The pullback domain's not given here, right? But you know, if I give you a tilted square and I ask you, how is this a rotation of something nicer? I mean, look, there's different ways that you can do it, I suppose, but sort of the easiest, most obvious way is to say, well, look, it's like I'm taking this domain here and I am rotating counterclockwise by an angle that I can see right there, or maybe even more conveniently, that I can see right there. All right, this is literally a counterclockwise rotation. And you do a little bit of geometry. I mean, look at the corresponding points and identify what that corresponding angle theta is. No big deal. Y'all know trig. That angle is pi over 6. Make sure that you can do that. Let me remind you, this course has a lot of prerequisites, and if you trace back through the prerequisite trail of this course, I'm going to assume that you are rock solid with trig, right? So, again, make sure that you can do that reliably. So having identified how I want to do this, then I know what that angle theta is, then I can write down explicitly what that rotation function is. That rotation by that angle, pi over 6. Here you go, and so there's my pullback. So now, from the context, I've decided on what I want my pullback domain to be, and I have found the corresponding change of variables function that does it. Okay, let me take a breath and a pause. Does anybody have any questions so far? We haven't done the change of variables pullback yet, but is everybody on board so far? Okie dokie. Well, it's all plug and chug from here. Well, we've got all of our necessary tools. Stretching factor, right? Absolute value of the Jacobian determinant. Well, there's that Jacobian determinant. It's a bunch of partials. Don't forget these individual, where does this come from? Well, if you look back at the definition of what this Jacobian determinant is, that's the partial of x with respect to u. And don't forget, we have a formula for x as a function of u and v. And computing that partial derivative is easy. Right? So don't forget, when you're computing your Jacobian determinant, the output variables as functions of the input variables are in your change of variables function. They're right there, right? So sometimes it's easy to forget this. Students will very often look at this and think, I don't see the x's. Right? But just don't forget what this function is. The whole purpose of this function is to take u and v as inputs and to give x and y as its outputs. Right? So make sure to remember. Anyway, this is one of these things that students very often forget. So, curiously, I'm going to say for a moment, check it out. The stretching factor is 1. Hey, weird. What are the odds? How about that? And then you recall, well, after all, we are talking about a rotation. And now let me just appeal to your sense of geometry. When you rotate things, you don't stretch them. There's no stretching involved in a rotation, right? If I could just turn my head to the side and all of a sudden everything looked bigger, wouldn't that be weird, right? So this is a highly satisfactory result. Now, let me point out, this is a math class. Furthermore, this is a class where one of the motivations that we have, one of our goals in this class is to make sure that you are good with the ideas and methods of, in particular, for example, change of variables, right? So on an exam in this course, please don't just make the geometric argument of, it's a rotation and therefore the stretching factor is 1. I want to see the explicit details. Okay, but nevertheless, I like sanity checks, and this is a nice sanity check. Okay, so we got our stretching factor, and now we're into the plug and chug method, the plug and chug portion of the process. Don't forget that x is right there, right? So you can plug in for what that x is. That's a function of u and v that you can just stick in there. Likewise, y. You can just stick in there. And to do some algebra, you got to square that formula for x and square that formula for y, and yada yada yada. Algebra to be done. Turns out that that integrand turns into u squared plus v squared, as it happens. Okay. And there's a geometric point of view on that as well. And again, let's not go down that bunny hole. Here's our stretching factor. Notice. Plug in your stretching factor. When you rewrite dx, dy, in terms of u's and v's, don't forget to stick in that stretching factor. It happens to be 1. I remind you, this isn't a course about answers. This is a course about ideas. If you do not indicate the computation of that factor of 1 and the inclusion of that 1 in your algebra, then it looks like you did not understand the necessity of that factor of 1. It happened to, it doesn't affect the answer, but it is part of the argument, right? Remember, the focus is on the argument. So make sure to show the fact that there's a 1 there. Right. Okay. All right. So notice the result is a super easy integral. We've got nice rectangular bounds. The integrand didn't even get any worse. Weird. Again, you won't always get that lucky, but hey, sometimes life is good. And certainly this is a much more desirable integral, mostly because of the bounds. Okay. I'm going to show you another example of where you can come up with a change of variables function. Here we inferred the change of variables function from a sort of a template, right? Rotations and understanding rotations and seeing how you can strategically take advantage of that. This next one, I'm going to have to lay a little bit of groundwork first. So bear with me for just a moment. Let's momentarily ignore this down here. Momentarily, let me remind you that when you have a change of variables function that gives x and y as functions of u's and v's, here's your formula for your stretching factor, right? And here's how you use that stretching factor. Oh, this is exactly what we've been doing so far. Nothing really just happened there. Okay. Notice, importantly, that the stretching factor is the partials of the output variables with respect to the input variables. Yeah? That's the rule. Partial of the output variables with respect to the input variables, where, I mean, that's the direction this function is going. This function is going what you might call left to right. So x and y are the outputs. U and v are the inputs. Okay, now with that noted, let me actually now momentarily scratch this off and let me erase all of this. Let's now reconceive. Let's suppose we were choosing, for whatever reason, don't worry about why, but let's just hypothetically, suppose I was thinking of U and V as being functions of X and Y. Now, it's a free country. They're just variable names, right? I mean, I could conceivably write down formulas that give me U and V as functions of X and Y. And the letters of the alphabet don't matter, right? The rule for how to compute a stretching factor is not partials of the late alphabet variables with respect to the earlier alphabet variables. That's not the rule, right? It's outputs with respect to inputs. So, thinking of a function going the other way, the partials of the output variables with respect to the input variables gives me partial uv, partial xy as my stretching factor. It's really the same statement that we made, just kind of letting the variables play opposite roles. Okay, so let's think then about the scenario we've got. We've got two functions now. We've got a change of variables function that goes to the right. We've got a different now change of variables function that goes to the left. And I see how these differentials, these pieces of areas, or this is a stretched out version of those, and those are stretched out versions of these. And notice then, if I just take this formula and put it right in there, I'm going to let y'all complete the algebra on that. But the punchline is this. A little bit of algebra, exercise for you. Nice punchline, though, is that the stretching factor going the one way is the reciprocal of the stretching factor going the other way. Yeah. Which, by the way, again, is a very satisfying, right? I mean, if the process of going this way stretches things out, I mean, turn that movie around backwards and going the other direction clearly squishes by the same factor as the stretches. I mean, it's highly believable. Right? Okay. All right. Just a little context there. Oh, and then real quick, I want to point out despite the fact that this is satisfying from that stretching and squishing point of view, I want to point out that this is not algebraically obvious. A lot of people look at that and say, oh yeah, sure, of course, that's how fractions work. These aren't fractions, right? I mean, let's take a moment to acknowledge off the cap that this thing here that we're playing around with, this, despite my notation, is a determinant. It is not a fraction, and you cannot argue fractional algebra about things that aren't fractions just because I choose to write them as fractions, right? It's not that this is true. Let me get back to it. It's not that this is true because they're fractions. Wrong. We choose to write them as fractions because this is true. Right? The motivation goes the other direction. They behave like fractions for highly non-obvious reasons, and so we choose to write them as fractions. Okay. That said, very convenient, right? The motivation for writing them as fractions is clear. I can treat them as fractions because they behave like fractions, so let's draw them as fractions. Okay. All right, so let's consider this example. This is a seemingly very weird example. I want to compute an integral over this domain here that's bounded by these four curves, and now we have a little bit of an algebra / graphing. Shame on me, I said graphing. These aren't graphs, these are level sets. -1 on my paper, right? These aren't graphs. But we have a equation drawing, solution set drawing problem in front of us. Let's draw these curves real quick. These two curves, whoops, I missed. Those two curves look vaguely, sort of, kind of like that. Those are hyperbolas, right? Algebra 2 flashbacks, right? These two curves here Vaguely hyperbola-like in a way, but not hyperbolas, because the algebra is just not the same. And I claim that those look qualitatively kind of like this. And you can make sense out of this by entertaining the question of, well, for example, what happens in these curves versus those curves when y gets large? Well, when y gets large, that factor gets extra large, which means that x coordinates get extra small. And you can see that in these curves, those x coordinates get extra small as y increases. And then you can make an analogous argument in understanding what's happening over here by thinking about what happens when x gets large, and the details for y'all. Okay, so a couple of weird curves, and now let's talk about the region in question. Our region is going to be the region that's bounded by those curves, and we're just looking at the part in the first quadrant. And it's that region right there. And that's a weird domain. Right? I mean, it's pretty weird as a domain. However you slice, there's going to be corners everywhere. And so if we were to need to compute an integral over that domain, right, highly undesirable. Right, now, before I go on and talk about how to actually compute this integral, it turns out there's a real slick way to do it with change of variables. Details to come momentarily, but I do want to talk about the example itself and where the example comes from. This looks highly manufactured. This looks artificial. And I just want to point out, especially to those engineers in the crowd, someday, as engineers, you're going to take a course in thermodynamics. And when you take a course in thermodynamics, you're going to learn about something called the Carnot Cycle or the Carnot engine. It's a very important theoretical concept. It's an imaginary sort of construction, but very important in understanding how to interpret, make sense out of the laws of thermodynamics. It's a really big deal. Right? And as it turns out, understanding the Carnot engine involves, it's hard to see this coming, and I'll leave that for your future engineering or physics classes, involves doing integrals over this domain. Right? So this is not a manufactured weirdo, me trying to make your life as difficult as possible type situation. This is extremely real world, extremely natural. And I will confess, tweaked the details a little bit. These exponents aren't 2s, they're weirder numbers. But for our mathematical purposes, it's fine. Okay. So, what is our change of variables function? Recall that the way we do change of variables is we try to view our undesirable domains as being images of more desirable domains. And that ends up not being clear exactly how to accomplish that. What we're going to do is go the other way. Now, this seems pointless initially, right? We're going to try to view the desirable, the new domain as being the image. We have not done that before, right? It seems like we're going the wrong way. Momentarily, just bear with me. Let's just go ahead and do this anyway. Let's come up with a formula that gives me u's and v's as functions of x and y. And here's the motivation for the function in question. Notice that if I want to write u's and v's as functions of x and y, I have some functions of x and y right in front of me. Right, here's some functions of x and y. So I don't know, just for lack of better ideas, let's take these existing functions of x and y, right? We're blindfolded. We're trying to hit the target with an arrow. Let's take the only thing that we have and hope that we hit the target, right? Hope that something good happens. So I'm going to take these functions of x and y, and I'm going to call them u and v. Fingers crossed. And then let's take advantage of the fact that these functions of x and y, these are not just random functions of x and y. These are functions of x and y that I'm setting equal to constants. And that's an important part of the scenario here. So by the way, if you have equations where you don't have, equals constant, shuffle things around in such a way that you have stuff equals constant. Those are the functions. It's very important that we are looking at level sets over here. So I've got functions of x and y equaling constants, notice that that means, for example, that I have u equals constants, and u equals constants are lines. I like lines, right? And then likewise, looking at these over here, these, if I'm setting xy squared equal to constants, then I am setting, therefore, v equal to constants. And therefore, again, lines. Right? So what I find is that this Hail Mary pass, shot in the dark, fingers crossed, hope something good happens, choice of a function gives us a new domain that's just a rectangle. And that's good news. We love rectangles. Big win. Okay. All right. Now, there is the little matter of how do we compute the stretching factor, right? I don't know how to compute the stretching factor going the wrong way. I know how to compute the stretching factor going that way. I don't know how to compute the stretching factor going that way. Oh, wait a minute. Yes, we do. It's just a reciprocal, right? So compute whichever, if you have u's and v's as functions of x and y, and if you want x's and y's as functions of u's and v's, right? So if this is the one that you have and this is the one that you want, cool, that's fine. Just take a reciprocal. Take the reciprocal that the fractional notation suggests that you should take anyway, right? And cool. Right? So that's exactly what we're going to do. So here we go. These allow me to compute those partials very easily. Easy determinant. Oh, wait a second. I want to know this instead. I need the pullback stretching factor going the other way. So, cool. I'll take the reciprocal of it. And that gives you your stretching factor. Everybody good? It's pretty sweet. By the way, here's another way to think about it. This is another sort of big advantage of the notation. In this process, I've got an integral over here, dx dy, and I'm trying to rewrite this as an integral blah 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 of du dv. And so there is this question of, oh gosh, which one do I put in here? What is the stretching factor? Do I want the stretching factor for okay, I know, but my function's going that way, but do I need it to go this way? And which way is the right way? And it's easy to get confused, right? The notation will straighten that all out for you. You don't have to remember, I'm going the opposite direction, and therefore the notation immediately makes it clear that what you've got to put in here is partial xy, partial uv. Again, there's this faux cancellation here, right? That, again, I get the willies every time I do that because this is not actually legitimate cancellation, but I do know that this is the victimless crime, that this is nonsense that will always guide you correctly. This is helpful nonsense, right? So, take advantage of the helpful nonsense. And that immediately tells you, just the nature of the algebra tells you that this is the one that I want. Right? And then you can sort of, again, algebraically recognize, well, yeah, but this is what I can compute, because those are the partial derivatives that I can see. And seeing that, I have the one, but I want the other, boom, you take the reciprocal, and life is good. So you don't even really have to think about the order. All right, here is an awkwardness I want to point out. This integral that we were trying to compute, this original integral over my undesirable domain, when you plug in the stretching factor that we just computed, here's our stretching factor, trying to rewrite x's and y's in terms of u's and v's. Notice that it's not in terms of u's and v's. Right? It's in terms of x's and y's, because that's the way it came. I computed it from the other direction, so it's in terms of the other variables, and that's unfortunate. Note further, I can't just plug in here. We'll just plug in for how I know that x's and y's are functions of u's and v's. I don't have x's and y's in terms of u's and v's. I have u's and v's in terms of x's and y's. So there is this ugly fact in front of us that I've got a couple of things that are in terms of x's and y's that I need to write in terms of u's and v's, and my algebra does not just let me immediately plug in. So this is a, the ugly underbelly of this clever strategy of just go the other way and take a reciprocal, right? I mean, the detailed devil is, how do you plug in? So I'm going to give you two answers to how to deal with that. One is sometimes you get lucky. Notice in this case, and by the way, maybe I should start by saying I don't really need to know these factors individually. I only actually really need to know their product. After all, I am multiplying them. So I can focus just on this. And so how would I rewrite xy in terms of u's and v's? Well, lucky break. That was given. All right, so look for the freebies. All right? Sometimes you get lucky. So there's that. If you didn't get lucky, then what you can do is speculate as follows. Let's suppose that instead of this, let's suppose you had some, product of powers of x's and y's, like that. What if that was your resulting sort of domain? And I want to know how to rewrite this product of powers of x's and y's in terms of u and v, which themselves are products of powers of x's and y's. And so speculate, right, based on the structure of the algebra. Okay, I have products of powers of x's and y's. I want to construct a different products of powers of x's and y's. What do you think what's going to make that happen? And a reasonable speculation is that maybe a product of powers of those products of powers of x's and y's might give me the needed product of powers of x's and y's, right? I mean, so that's just kind of the way the algebra kind of suggested in this case. This just seems like a good thing to try. Don't try cosecant in this scenario, right? That doesn't look like that's how you make these Legos fit together, right? So I can't make this precise. I can't give you here's the hopper. Toss your raw materials into this hopper and turn the crank, and out comes the answer. Right? But this is the kind of pattern that you can kind of look for and speculate. Okay. All right. And then so having speculated about your form, you can then solve for the necessary A's and B's. A little bit of Algebra 1 stuff there. Okay, I'm going to go extremely quick through the three-dimensional version of change of variables. Moral being, because it's exactly the same. It is so the same as the two-dimensional change of variables. So let me just walk you through it real quick. Let's suppose I have some ugly domain. I mean, just some nasty domain like that. Let's take a moment in horror to think about how nightmarish it would be if I were to start taking slices, nice flat planar slices in the XYZ space of this nightmarish domain. I'm going to hit a lot of corners. I'm going to sideswipe a lot of faces, and I'm just going to have unthinkably many pieces that I would have to break this up into because of just structurally how the slices look. Right? So nightmarish, but if I can view that as being an image of a nicer domain, then I can make a pullback argument, right? And all I have to do is figure out the stretching factor. I just have to think about, okay, well, if I have a piece of the domain over here, that's going to have an image which is maybe a little bigger over there, and I just need to know how much do things get stretched out. Just need a formula for our stretching factor. Here it is. That formula for the stretching factor. It's the exact same formula. It's the absolute value of the Jacobian determinant. For reasons that we will eventually see are, in fact, morally exactly the same reasons. Now, again, I haven't given you any of those reasons yet, but they are highly analogous. So, punchline, exact same deal, right? So here's an example I'm going to let y'all read, but notice in this example the change of variables function is given. Let me recognize that, sometimes identifying a good change of variables function, it's all the harder in 3 dimensions because even in 2 dimensions there's this, this collection of cases that we sort of cling to, but we don't have an all-encompassing method, right? So here, same story, plus added geometric sort of challenge of visualization, right? So it's hard. So anyway, in this example here, it's given, and Jacobian determinant, plug in Chug, there's our stretching factor, and everything else is a matter of plugging in. Our dx, dy, dz is stretching factor times du, dv, dw. Everything else is plugging in details. Okay, so I'm just going to let y'all read the rest of that. There's some examples in the book. The ideas are really all the same. Okay, so I want to go back to symmetry. Y'all remember this very powerful idea of symmetry, using symmetry to compute integrals. The argument that I gave for that was a Riemann sum argument, and then I made a vague reference to how, you can actually also make a something like a substitution argument that we'll see later. Here's later. So here I'm going to show you how to use, in fact, the change of variables rule change of variables method to make that argument. Okay, I am going to rely on the fact that reflections have a stretching factor of 1. Now again, in a homework or exam setting, I don't want y'all to just cite reflections always have a stretching factor of 1. I want to see the calculation. But here in this context, I'm just going to assert that this is true. I do think this is highly plausible. And by the way, if anyone wants to really see a proof, I'm happy to show you. It's a matter, the hardest part of proving this is to just write down a formula for a generic reflection. It's not that big a deal. In fact, you could take this as an exercise if you're interested. This is a chapter 12 exercise to write down a generic formula for a reflection through a line. Let's keep it 2-dimensional. Reflection through an arbitrary line. How do you write down that formula? And then compute its Jacobian determinant. It's not that hard. Anyway, you can feel free to give it a try. Feel free to ask me in office hours. Feel free to just trust me. Okay, so that being said, I claim that if you use a reflection as a change of variables function, the symmetry theorem drops into our lap. It's wonderfully convenient how this works. Let me show you how this works. Suppose we're interested in this integral. We are going to, now keep in mind, we're assuming that our domain is symmetric, and the domain being symmetric means that it is its own reflection. That's what symmetry is. Right? Rorschach, pictures, etc. Right? It is its own reflection. Okay, now notice I have here an integral over an image. When you have an integral over an image, you can do a change of variables, and an integral over an image using change of variables, we pull back the domain. We're using our reflection as our change of variables function. Pull back the domain. The pre-image of the reflection is the original domain. That's how you reverse engineer a reflection, right? The undoing of a reflection is, in fact, the same reflection. Again, that's how reflections work. Right? And the stretching factor is 1. Right? So area gets stretched out by that factor of 1. Okay? Now, don't forget, the other assumption not only is the domain symmetric, but furthermore, the function in question is odd. Because the function is odd, I can rewrite f at the reflection as a negative of f at the original point. And it's all over but the shouting. You move this minus sign over to here, and check it out. This integral that I'm interested in is its own negative, and therefore is 0. It's a sweet little argument, right? Very cool. And again, relies critically on change of variables and this pullback from an image domain to a pre-image domain. So lovely argument. So anyway, for your consideration. Very analogous argument for triple integrals. I'll let y'all think through the detail. How would the details change? And by the way, it's not very much. It's just really kind of the superficial details. But nevertheless, it's healthy exercise to think it through. How would you do this for triple integrals? Okay. Let me pause again, take a breath. Does anybody have any questions? Everybody's good? All right. Okie dokie. Okay, so we're about now to, let me remind you, we are bouncing around through chapter 14. 14.9 that we just finished is at the very end of chapter 14, and now we're going to bounce all the way back to, I think this is section 10.2 that we're going to do, and the reason we're doing 10.2 is so that we can do other things with the polar coordinates that we're about to study, and just foreshadowing. What we're going to do with polar coordinates is we're going to use them as a change of variables function, as it turns out. There's really powerful things happen when you take polar coordinates and use them as a change of variables function. Okay, that's something to be looking for. Look for hints of that as we go along. Okay, so start off with rectangular coordinates. I claim that rectangular coordinates are unique, by which I mean if you give me a point in R2, it has rectangular coordinates and vice versa, and there's for every point, there's exactly one set of coordinates. For every set of coordinates, there's exactly one point. We have a perfect pairing between points and rectangular coordinates. So rectangular coordinates are unique. Polar coordinates are not. So I'm going to give you a different way to think about polar coordinates. Now, if you haven't seen polar coordinates before, no problem. No problem. If you have seen polar coordinates before, okay, cool, but set that aside, please, because I do want you to take this new point of view this is important new point of view that's going to help us do things with them later on. So please don't try to fit what I'm doing here into your high school point of view on polar coordinates. Please kind of set aside. Let me give you a new foundational point of view on polar coordinates. So here's the idea. Polar coordinates, I want you to think of them as a function. In some sense, we're not even really going to think of them as coordinates exactly, but think of polar coordinates as a function. So specifically, we've got a function, and the domain is going to be the r theta plane. Don't worry about why we're calling them r and theta just this moment, but if you give me an r and a theta, then out is going to come, I used the wrong color. I wanted that to be purple. If you give me an r and a theta, which you might think of as a point in the r theta plane, then out comes a point in R2. And that point in the xy plane is determined as follows. Whatever the theta is, I'm going to say that defines a direction. And it defines that direction specifically by starting on the positive portion of the x-axis and rotating counterclockwise in the amount given by that, whatever that theta is. Okay, so it's an angle. Rotate by that angle. That defines a direction. Okay. Secondly, this r thing, this variable. All right, so we've got theta sort of defined. R says how far, note the quotes, how far to go in that direction. So if you got an R like that, for example, that says you go that far. And notice that that defines a point in the xy plane. Right? You give me any R and any theta. Follow these instructions for what to do with that R and that theta, and out comes a location in the xy plane and therefore a point in the xy plane. Little detail. Why did I put how far in quotes? So I put how far in quotes because I want to recognize, let me just erase all this, that the R could be negative, right? So I've got this direction defined And if r is positive, I'm going to say like this. Oh, here, I guess I should do it like if r is positive, then yeah, go positive means go in that direction by that far. And if r is negative, I just mean go in the other direction. Right? So how far in quotes. Okay. Yep.
When theta is negative, does it?
Yeah, just go the other way. Yeah, theta just goes backwards. Right. So think of the negative of counterclockwise as being clockwise. Yeah. So, and think of the negative of forward as being backward. This is pretty believable.
So positive theta is counterclockwise.
Positive is counterclockwise. That's an arbitrary but standard convention. That's right. Absolutely. Okay. Okay, so notice, very importantly, this is a function. I want you to think of these polar coordinates as being this function. And I know you may have a different point of view on the r and the theta, and let's, this is going to be important in what we're doing. Okay, now there's a lot of little details that ensue. Not hard to persuade yourself from drawing a picture, a little bit of trig, and I'm going to leave as an exercise for y'all to do on your own. Draw that triangle, that right triangle, and persuade yourself that x is our cosine theta, and y is our sine theta. Just a little trig. Y'all can do that. Easy argument. And so now we have an explicit formula for our polar coordinates function. So I'm going to call this the polar coordinates function. Okay. All right. So some little details to talk through. Polar coordinates, conceived of as we've described here, not unique. Notice that thinking of this point as being that direction, with that distance, thus giving me that point, thinking of that as, well, a small angle and a positive distance in that direction would give me sort of this r and theta coordinates for that point. But notice, that's going to seem silly, but if I were to define my direction by going a full 2 pi around and then that little bit further, that defines the same direction. Right? It seems weird, but that does define the same direction, and so this other point, right, theta plus 2 pi, the original theta plus 2 pi, it gives me the same point. And I can do as many 2 pi's as I want. I could do, each time you add 2 pi to the angle, you're just doing an additional loop around. That, of course, doesn't really change the direction. And you can subtract 2 pi as well. Okay. And there's a weird one. You can also do sort of half turns. This is going to seem very weird, but if I want to go that way, one thing I could do is do an extra half turn, thus defining the opposite direction, and then in that opposite direction, I go a negative amount. Backwards, right? If this is if that's the direction that I'm defining, then the backwards direction is in fact the direction that I actually kind of wanted to go. So it gets me to the same point. So that gives me, for example, that extra pi, right? Gives me these other points over here with, again, notice negative values of r. And again, plus 2 pi all you want, minus 2 pi all you want on the angle. So highly non-unique. Weird, awkward, annoying. Be careful. Another little micro thing, and let me not go too slow on this, but when you write down a point, sometimes it's not clear what are you talking about there. So this point I write down 1 comma pi over 6, and cosmetically you're like, oh hey, pi over 6, that kind of looks like an angle. So this is probably r comma theta, right? But let's just take a moment to recognize there is a point where x is 1 and y is pi over 6. Right? So if you just write down 1 comma pi over 6, it's really not, in fact, immediately clear what you're talking about. So be careful with how you write things down. If it is not blatantly obvious what you mean, clarify, right? And so, for example, writing R equals theta equals, that's unambiguous. Likewise, this is unambiguous. That's cool, right? So don't be too sloppy with that. And lastly, let me do this really quick because it's really quick. Converting back is dangerous. Now, it's easy to persuade yourself of these rules relating R's and thetas and X's and Y's, right? It's very tempting to solve, air quotes, for R and say R is the square root of X squared plus Y squared. Nope. That would suggest, after all, if you write R equals square root, that would suggest R has to be positive. It does not. Likewise, if you were to solve for theta here and say, hey, theta is the arctangent of Y over X, no, that would suggest that theta is always within a certain range of angles. There is no such constraint on theta. And here's a scary little scary little landmine you can step on. If you look at this point here, right, with coordinates -1, -1, if you just play the naive game of, R is the square root and theta is the arctangent, notice that you'll write down blindly, naively, that R is square root of 2 and theta is pi over 4. And theta pi over 4 is like this. R square root of 2 would put me right there. And that is not the point I want. Right? I want to be over here. So, heads up. You just can't. It's just wrong to say theta is the arctangent and R is the square root. Be super duper careful. R could be either this or that. Theta could be either this or that. And then you've got to look at the geometry of the situation and think about, well, wait a minute, how do of all my possible different ways that I could describe this point in polar coordinates, which one do I really want? And what actually makes sense? And so this point of view, right, you can see that we're clearly choosing that value of theta to pair with that positive R. Or if you want to be, backwards about it, if you want to think about it from the point of view where the angle is pi over 4, okay, but then you have to let your R be negative square root of 2 to get to where you actually want to go. Okay, let me call it a day. Let you talk to me after class, and see y'all later. Have a great weekend. Yeah.